Welcome back. This is part two of the problem set that I gave out the other day in class, Friday that would be. And we're going to solve problems 5, 6, 7, and 8 on this video. Let's start with what is problem 5. It says a force of 146 newtons is applied to a 12 kilogram box sitting on a frictionless surface. The box, originally at rest, now has a velocity of 7 meters a second. How much work was done to the box? There's actually a couple of different ways to solve this problem. I'm forever telling you guys that that conservation of energy is just one more tool to put in the toolbox. Well, we can use that tool, or we can use the tool that is kinematic. So let me first start with kinematics, and then I'll show you the better and easier way to solve this. The work done as this force is applied to this box and causes some movement is, of course, work is force times displacement times cosine of theta. Well, we know a lot of things. We know that it started at rest. We know that its velocity is 7 meters per second now. We may know enough to do kinematics on this. We know the force here, it's 146 newtons. If we can figure out the distance that it travels, then we can figure out the work. Well, so let's plow down that road and see what happens. As I said, you can solve this using kinematics, so let's do that real quick. We want to know what the displacement is. We're going to not care about time. The problem said the starting velocity, it was at rest, so that's 0 meters per second. And later, it's 7 meters per second. Now, that's only two things, and I've always told you you have to know 3 of these things, or you can't do the kinematics. But it turns out, finding out the acceleration that the 12 kilogram box had would be pretty easy, because that force caused that mass to have some acceleration. It's just Newton's second law. So we plug in what we know. We know that the force was 146 newtons, and it caused a mass of 12 kilograms to have some acceleration. When you work that out, you find out that the acceleration of the thing was 12.17 meters per second squared. So now I can solve a kinematic problem to find displacement. Once I know displacement, I can plug it into the work formula and find out how much work was done. Well, let's see. Not caring about time leads me to Helen. Sticking the numbers in here, it was pre-solved for us. So velocity later is 7 meters a second. Initial velocity was 0 meters a second. Over 2 times this acceleration that we determined it had, 12.17. When I crank through that math, I find that it travels 2.01 meters while this work is being done to it. So that's my delta D. Now we just stick that into here. I've got the force of 146 newtons, the displacement of 201, and the cosine of the angle. Well, it's the angle between the displacement and the force. A force of 146 newtons is applied to a box sitting on a frictionless surface. So that means that all of the force is acting in the direction of the displacement. So that would be cosine of 0. When I crank that out, I get that 294 joules worth of work was done. That is one way to do this. I want to show you a different way, I'd say a little more eloquent way. Amongst the things I've told you about work, the total work done to something, regardless whether there's 1 or 2 or 100 forces acting on it, the total work is really the change in kinetic energy, the final kinetic energy minus the initial kinetic energy. The total work is 1/2 mv later squared minus 1/2 mv starting squared. This is the kinetic energy later minus the kinetic energy initially, and we know the velocity later, it's 15 meters a second. The velocity at the starting was 0 meters a second. So you stick that in there because this is a 0 meters per second here. This whole second term's going to equal a 0. So I just do this one math here, 1/2 times 12 kilograms times 15 meters per second squared comes out to 294. Now, here's the point I want to make. All of this math is how we do it using kinematics. This is how we use it doing conservation of energy. Conservation of energy is a much more efficient way to calculate. The arithmetic is a whole lot easier, and both of them get us to the exact same place. Because, again, kinematics is a tool, conservation of energy is a tool. They are just different tools to use. Sometimes both tools work on a given problem. Sometimes you need one of them or the other. All right, let's see what's next. Problem 6 says, Problem 6 says the Earth has a mass of 5.97 times 10 to the 24 kilograms. The mass of the Moon is 7.35 times 10 to the 22 kilograms. They are separated by 3.84 times 10 to the 8 meters. If your 1,000 kilogram rocket ship is halfway to the Moon, what force would it feel? Well, that's actually asking what net force, because your rocket would feel a force from gravity pulling it back towards Earth and a force from the Moon pulling it towards the Moon. And our job is to see how those forces add up. So we're going to have to find each one separately. The distance to the Moon is 3.84 times 10 to the 8th. And so the half that distance, the distance you are, is 1.92 times 10 to the 8th. You are that distance from the Earth. You're at the halfway point. So you're that distance to the Moon also. So all we have to do is insert these into the formula for universal gravitation, and we should be home free. That formula, you'll recall, is the force is equal to G m1 times m2 over r squared. We're going to do first the force of the Earth pulling the rocket ship backwards. So we stick the numbers in here. That's G is this number that I have to give you. We discovered it or measured it in the lab. 6.67 times 10 to the 11. That's not written correctly, but you all know what it's supposed to be. And the mass is of the Earth, m1, 5.97 times 10 to the 24. The mass of you is 1,000 kilograms. So it's the mass of the Earth and the mass of you. That's the force that the Earth is creating on you. And then in my denominator, I put r squared, the distance it is from the Earth, 1.92 times 10 to the 8th squared. You work all that out on your calculator. We've talked about how to do that in class. And it comes out to 10.8 newtons. The Earth is pulling back on you with a force of 10.8 newtons. The Moon, on the other hand, is the formula for the Moon, and we stick the numbers in there. I won't bother belaboring us with that. We just took the mass of the Earth out and put the mass of the Moon in there, along with the mass of the rocket ship. And that turns out to be 0.13 newtons. So Earth is pulling you backwards with 10.8 newtons. And the Moon is pulling you forward at 0.13 newtons. So your job is to find the net force. The total force is just how the Earth is pulling you plus how the Moon is pulling you. But of course, one of those has to be negative because they're pulling in opposite directions. So 10.80 minus 0.13 is a net force towards the Earth of 10.67. That's all there is to solving that. Problem 7 says, a snow skier with a mass of 62 kilograms is skiing in level ground at a speed of 6.3 meters per second when he comes upon a 1.2 meter hill. Ignoring friction, what is his speed at the top of the hill? Okay, it says ignoring friction, so we're going to find his mechanical energy at the bottom of the hill. It's going to be the same as his mechanical energy at the top of the hill because there's no friction, and we're going to use that to solve his velocity. So we need to get the equation out here for mechanical energy. The potential plus kinetic at any one location is the same as it is at any other location if there is no friction. So it's potential plus kinetic, and of course potential is m a sub g times h. Kinetic is 1/2 mv squared. Let's plug in what we know at the bottom of the hill. Let's see, we know that there is no potential energy because he can't fall any further than the bottom of the hill. And then the kinetic energy is 1/2 his mass, 62 kilograms, times his speed, 6.3 meters per second squared. You work that out on your calculator and you get that his mechanical energy at the bottom of the hill is 1,230.4. That will be his mechanical energy at the top of the hill. So we just set it equal to that. We figure out what else we know. We've got potential energy of 62 kilograms times 10 meters per second squared times the height of the hill, 1.2 meters. That's the delta x, change in x, plus the kinetic energy, 1/2 the mass, 62 kilograms, times the velocity squared. We know everything in that. We grab our calculators and solve for v squared, and the answer comes out to 3.96 meters per second. That's all there is to that one.